Okay, welcome to the Spotlight session. And the first speaker today is Julian Mairal, who's going to talk about convolutional kernel networks.
Thank you. So as the title may suggest, so this work is about happy marriage between kernels and convolutional kernel neural networks. And this is a joint work with my colleagues from INRIA Grenoble, so Piotr Koniusz, Harchaoui, and Schmid. So in short, we are interested in kernels that operate directly on images and that have some invariant properties, and that has also been shown in the past to be particularly effective for image classification tasks. So these kernels are relatively powerful, but unfortunately they are very computationally expensive, and so they require approximations to be used in practice, and this is what this work is about. So what becomes interesting is that the approximation scheme that we develop turns out to be a new type of convolutional neural network, which has the following properties. So learning is unsupervised, so which means that the network is trained to approximate the kernel. Then every aspect of the network, such as nonlinearities, have the purpose of approximating the kernel, and at the end, the network that we obtain approximately works in a reproducing kernel Hilbert space. So the main component of these kernels are the concept of image feature map, which are maps that represent local information in the image, where every point on the map is a point in a Hilbert space. So when you have two image feature maps that represent two images, you may define a kernel that is represented here that compares the maps, and then you can go further and define a hierarchy of image feature maps, which are presented on the left, where if you take a point on a feature map at layer K, it basically represents information from a patch from the previous layer. So these are points in a Hilbert spaces. Now the approximation scheme provides finite dimensional maps, which are on the right. And on the right, we see that the approximation scheme that we have is in fact convolutional neural networks where we have convolutions with nonlinearities plus a pooling step. So interestingly, the nonlinearities that we have in this network that emerge from the approximation that are not designed by hand, in fact, are relatively similar to rectified linear units. And also, we achieve with these networks competitive performance on classical datasets such as MNIST, Cypher10, and STL10, with actually very few efforts. So I believe that we are at the stage of proof of concept, but we open nice perspectives. Thank you.
Thank you, Julian. And now we have Zhou, who's going to talk about learning deep features.
Hi, I'm Zhou from MIT. This is joint work with Akta, Zhenzhong, Antonio, and Ott. So in this work, we build up a large-scale image dataset called places for scene recognition. Scene recognition is one of the long-standing problems in computer vision. It provides a special context for object recognition. Here we define scene recognition. Given an image, our goal is to recognize which place we are in, whether we are in kitchen, living room, or we are in a conference center. The early image dataset for scene recognition is a 15-scene database proposed in 2005. It only contains 1,000 images and 15 scene categories. In 2010, it came the Sun database, which contains 100,000 images. It was still not sufficient to train a deep neural network. Here comes the Places database. Till now, the Places database has 7 million images. From the histogram of image numbers in each scene categories for Places, ImageNet, and Sun, you can see the Places database is the largest scene database so far. Though we are the largest scene database, a 2-year-old kid still saw 100 times larger number of scene images on our database. Besides the large image numbers, Places database also has a high diversity of image content. We use a combination of 600 adjectives plus scene names to retrieve images from image search engines. Those downloaded images are further sent to Amazon Machine Network for annotations. Here are image samples from several types of bedrooms. For example, in the messy bedroom, there are a lot of random stuff inside. And for the crazy bedroom, there are a lot of animals and people inside. We believe that image with high diversity will help us train a scene recognition system that could really work in real life. So we train a convolutional neural network on places database. So the training set contains 2.5 million images from 205 categories with same architecture with imageless CNNs. We evaluate place CNN on the test set of places and the corresponding scene category in sum. The places CNN have the state-of-the-art performers, outperforming imageless CNN features plus SVM in large margins. So the data and pre-trained network are available at our project page. You also could access demo of scene recognition there. Here are 3 snapshots of our demos. 3 images are predicted successfully as coffee shop, supermarket, and conference center. I encourage you to play with the demo and give us some feedback. To understand the database, how the network works, and why it works, please come to our poster session tonight. Thank you.
Thank you, Bole. And the next up is Wojciech Zaremba, who's going to talk about learning mathematical identities.
Hello, everyone. My name is Wojciech Zaremba. I will be speaking about learning mathematical identities. It's a work conducted with my collaborators, Kurach and Fergus. So you heard today already from Ilya that actually most of the problems in vision and NLP can be brute force in the sense that we can collect tons of data, build big enough neural networks, and to some extent we are able to solve such problems. So I started to get interested in more difficult problems in which there is no even way to collect data. Those are like most difficult problems in reasoning, which is essentially how to prove things in mathematics. So I believe that actually mathematicians, they learn over the time prior over the proofs, which allows them to actually solve other problems. So you can think that every proof gives you a prior about how the proofs should look like. So that's what the mathematicians do. They just learn the prior. So we consider like some smallest possible, like some easy branch of mathematics where we are able easily to enumerate some proofs and so on. These branches, those are identities over the matrices. Those are some constrained identities over matrices. And we are able to find new mathematical identities which are sort of beyond my comprehension. I'm not able to prove them. My computer was able to prove them for me. Here is an example. Actually, it goes for few more pages of the mathematical identity, which is maybe it looked a little bit clumsy and so on. I had no way to prove the identity itself, but it turned out to be much faster than the initial target expression. We train our models in the same way as you, let's say, teach kids. We start with simple problems to solve, and we move to the more difficult one. And we actually use very basic techniques from NLP and from NLP, like n-grams and so on. So we learn the distribution over the kind of the proofs or over the mathematical expressions which make sense using simple NLP techniques. Thank you.
Thank you, Wojciech. And next up is Peter Sadowski, who's going to talk about searching for Higgs boson decay modes.
This is work with Pierre Baldi and Daniel Whiteson at UC Irvine. The Large Hadron Collider is the largest particle accelerator in the world, and it allows physicists to study the subatomic particles generated by high-energy proton collisions. The ATLAS detector shown here has 100 million sensors for detecting the products of these collisions and produces 1 petabyte of raw data per second. Physicists rely on machine learning to analyze this data. Earlier this year, we demonstrated that deep learning increases the statistical power of the analysis, improving upon the shallow learning algorithms that are widely used by the high-energy physics community. In this work, we focus on one type of Higgs boson decay that is of great interest, and demonstrate that deep learning requires less experimental data to achieve statistical significance. One of the top priorities in high-energy physics today is to obtain evidence of the Higgs boson decay, to obtain evidence that the Higgs boson decays into fermions, which is shown here on the left. This is a prediction of the standard model of physics. The data from 2012 provides limited evidence that this decay occurs, but it fails to meet the threshold of 5 sigma significance. Higgs decay events are difficult to observe because they are very rare, and background processes like the one shown can produce the same set of detectable particles. However, each type of decay has its own signature. To learn these signatures, we train machine learning classifiers on millions of simulated collisions. Then we use these classifiers to analyze the experimental data from the collider. The features used in this classification problem include direct measurements from the detector, as well as complex high-level features engineered by physicists that incorporate domain knowledge. Our work shows how deep neural networks perform better than shallow networks in detecting the Higgs decay to fermions. The deep networks both improve classification accuracy and increase discovery significance in the statistical analysis. The result is a 20% reduction in the amount of experimental data needed to reach the same significance level. For more information, please come to our poster. Thank you.
Thank you, Peter. And next we have Kingma, who's going to talk about semi-supervised learning with deep generative models.
Hello, everyone. This is work with Max Welling in Amsterdam and Shakir and Danilo at Google DeepMind in London. One of the most common problems in machine learning is that of semi-supervised learning, where we wish to learn a classifier, but not all of the data points are labeled. So how to make optimal use of both the labeled and the unlabeled data? We introduce a principled probabilistic approach to semi-supervised learning that is very powerful and can be used in combination with almost any existing deep learning classifier. So how does it work? A classifier learns the function from the input x, for example images, to class labels y. However, a more realistic model of how the data was generated was that the class label came first, and then the input image x was generated from the label and other latent variables z. So what we do is we introduce a generative model that we parameterize with deep neural networks that actually learns this function from the label and other latent variables to the input x. To learn the parameters of this function, we're going to need to do posterior inference over the latent variables, which is also the label in case of the unlabeled data. And we're going to use the classifier to do this approximate posterior inference. So the classifier not only needs to do the correct classification for the labeled data, it also needs to do the correct approximate posterior inference for the unlabeled data. And this second purpose acts as an effective regularizer for the classification model, leading to much lower prediction error on new data. Our method is also very efficient and scalable because of recent advances in stochastic variational inference and stochastic backpropagation. All that is required is the optimization of a single objective function using standard stochastic gradient descent. It's very simple. We see that in experiments, we often need about an order of magnitude less labeled data than other approaches to get good classification error. For example, on MNIST, where we have only 10 labels per class, we reach an error of only 3%, while the previous state of the art was 12% error. So that's a pretty large reduction, and we also see good results on other benchmarks. What is also cool is that we can do very successfully analogical reasoning using our efficient approximate inference methods. For example, you can take an image, then you can infer the style and the class, then you can change the class label and generate the whole sequence of images that looks like the input image, but just has a different class label. So this is a form of analogical reasoning. So for more information on our approach to semi-supervised learning, that is very flexible and powerful and can be applied to almost any existing classification model, please see our poster. Thank you very much.
Thank you, Diederik. And last we have Karen Simonyan, who is going to talk about two-stream convolutional networks.
Hi, It's not a secret that deep convolutional networks achieve excellent results on image recognition benchmarks. However, it is less clear what is the right deep architecture for video recognition tasks, such as action classification. And that is the problem which we address in our work. One of the key challenges in video classification is how to incorporate the temporal information. And the most previous deep architectures for video do it by operating on a stack of video frames. But our approach is different. We propose a coordinate architecture which contains two streams, the temporal stream, which accounts for motion, and the spatial stream, which accounts for appearance. And in the end, the predictions from temporal and spatial stream are combined by late fusion. So this is what our architecture looks like. The spatial stream predicts action from a single frame. So it's effectively an image classification task. So we can exploit large annotated collections of images to pre-train the spatial stream. And we do it on the ImageNet Challenge dataset. The temporal stream operates on motion data in the form of multi-frame optical flow, which is essentially a stack of displacement vector fields between consecutive frames of video. On the right, you can see the visualization of the optical flow between a pair of frames, which depicts a moving hand. And as can be seen, the hand is quite clearly visible on these visualizations. At test time, the spatial stream is applied to a number of frames evenly sampled in the video, and the prediction scores are then averaged. Similarly, the temporal stream is applied to a number of fixed-length fragments of video. And in the end, the predictions of a spatial stream and temporal stream are fused either by averaging or by learning an additional linear model on top of the scores. The data sets which we consider in this work, UCF 101 and HMDB 51, they're quite small, so overfitting is an issue. And one way to reduce it would be to combine these data sets, but doing it in a naive way leads to poor performance due to semantic overlap. So what we do here, we use multitask learning formulation, where there is a separate task for each of the data sets, and it works well. So if you have a look at the results, the temporal stream performs better than the spatial stream, which indicates that at least on these two data sets, motion is more informative than appearance. And when we combine spatial and temporal streams, the performance improves even further, which confirms that motion and appearance are complementary. Our results are better than previous attempts to use deep networks for video classification, and our results are very competitive with the best encapsulated features in spite of the limited training data. To conclude, we propose a two-stream coordinate architecture for video classification, which exploits complementary motion and appearance cues. Thank you.
Thank you, and this concludes the spotlight session.
Thanks very much. That also concludes the oral program for today. So the posters continue at 7. And if we could just thank all the presenters, all the session chairs, and the spotlight chairs for a great job on the first day's session.